Hello everyone, it's August 23rd. I got the title wrong. 23rd. Alright, it was pretty bad last night. And, man, I think I said in the past, never gonna do this thing again, but I did it again. More than 5 hours. So, no, this is not gonna happen again. We're gonna do 1 hour, or at least it's one attempt, right? You get one attempt, and if there's no, it's always about if there's no light at the end of the tunnel, we should just give up. There's no hard feelings. All right, anyway, let's go for today. To sum 4. Input is a BST. Given a root of a binary search tree and a target number k, return true if there exist two elements in the BST such that their sum is equal to the given target. So binary search tree, so it's going to be for one thing, you can just traverse the tree to obtain all the values, right? And then the requirements. Root is going to be a valid binary tree, search tree. It has no requirements. So, we can just turn the binary search tree into a list and then do the list. But I'm pretty sure we can just do binary search tree itself because it's binary search tree, right? So we can say, get the first value, right? And then we have a k, so I can k minus this value, like a 9, so minus 5 is a 4. So we search on this, search for 4. Basically, we use search. And if we find it, that's good. If we did not find it, we can go left and right. And if we go left and we do minus, and we can also record the parent, right? So like, it's 6. Oh, 6. Oh, we have to always search from the front, from the start. So we just traverse the tree. Traverse the tree will hit every single one's on, and then to find we on log n to find this. Right? Like, what's the point of having it as a binary search tree? I say, like, make it easier to find. But you still have to go through every single one to find it. And we start with here, 28, and then we go this, right? And like we need to look for 23, and we're here, larger, here, and nothing. And then what? And then, well, we know the smallest and we know the largest as we go through. So like here, we know the largest is 7, and so it's not possible. How do we use the binary search tree, like the best way of using it? The best way is just turn this into a dictionary. Turn this into a dictionary, I think, is the best way. Not a dictionary, turn this into a set. We traverse the binary search tree, turn it into a set, and then just go with a set. But again, can we do that? They say I probably can because it's 10 to the 4th. Well, that's fine. On, we grab all the numbers out, and then we go through every single one and just check. I feel like if we do binary search trees, it can actually make things slower. I mean, are you saying we don't have to hit every single value? If we go 5, right? We go from the root, and then hold on. We have a k, right? We have a k, and we check the root, and the root will tell us where to go if we use the root. And then we can say search from, I mean, the only thing is just like you have to check every single value, and for each value, you have to search from the front. I feel like we're doing a lot of repeated search. Like for 3, I say I want to search for 6, and then we go here, and we find it. And for 2, we say we want to find 7. Or the purpose of this is we can get a sorted order, right? We do on to get a sorted string, sorted array, and then it'll be easier for us to find. Well, how would it be easier for us to find? I don't think so. Because we don't need it to be sorted. Like in this case, right? Well, in this case, we'll find immediately. In this case, we just choose 5, and it's no good. Oh, hold on. Here's the trick. If 5 is no good, which means nothing, which means it's too small, all right? We can identify with that, which is 5. Now we need to find 23, and then this and this, we ended on the right, which means it's too small, too big. And then we don't have to go this route because we know 5 is no good. So we just go this, right? And then it's still too small. And we go this, it's still too small. So we only go one branch. Maybe that is the trick. We go one branch. So like for a certain value, we start, and then we go whichever way. Like for 5, we need something that's smaller. So we go small, and boom, like whether we find it or not, depending on if we end up, like we will only do this if we end up at something too small, right? If 5 is too big, right? If it's too big, and then we'll end up at the left. And then we can say, okay, it's too big, so the next one we need to go smaller, so we go here. But what if we don't find it? Right? What if we don't find it? Well, if we don't find it, I don't understand why we use binary search tree for this. Doesn't make any sense to me. All right, so let's try this 2, 1, 3, right? 2, 1, 3. So 2 is too big, so we go for 1, right? And 1 is still too big, then we go for, oh, nothing. We end. Yeah, so can we say value is too big or too small? Well, only if we AND on the left or on the right can we say this. If we don't AND there, then there's no saying. Right, this is what we know we can say, but if it's another value, let's say 10. 10, we need 5. Wait, where do we find 5? We have to, wait, what's the rule? What's the rule of binary search tree? I don't know. Let me try can we do a 5? See, instead of 6, can we do 5 here? Is this one legal? No repeats. No repeats. Okay, so that will not happen. So it must be something. Oh yeah, if there's no repeats, then if it's repeating, then it's no good. Then where do we go? We have to go both sides. Maybe that is the case. That you try one value, right, and then based on the result, you know what? I think it's just too convoluted. I don't know. What's the benefit of having a binary tree? No point. I'll just turn that into a counter. I think a counter is the one we want. Right, because we need to keep track on how many each value is. Oh, we don't even need a counter because it's unique. So no, we don't need this. It's just going to be a set. Just keep all the values in a set. Yeah, I don't understand. So vals equals a set, all right, and DFS node, tree node, option tree node, optional tree node, all right, and none if node vals.add node.val and DFS node.left, DFS node.right. I probably have like something like O1 space, and then for v in vals, if k minus v in vals, return true, otherwise return false. We're now gonna have test case. I'm just gonna run this. All right, this is not valid, so I'm gonna turn this into a 6, I think. Yeah. Huh? What the heck? What? My answer is false. Wait. Oh, I did not run DFS. That happened to me all the time. I forgot to run it. Yeah. Yeah, I don't see any. I think it should be it. Oh, I got a wrong answer. What the heck? Alright, I'm gonna redo this. Which one? Oh, it's the same thing. 28. Probably single one. Oh, oh yes, I know which one. If this is not equal to v and k minus v invals, right? Because they cannot be equal. Yeah, I think this shall be right. Yep, this is right. Yeah, I have to avoid this, so this has to be not to v and k minus v inval. It's like on. Yeah, this is like on. We did not use BST at all. We simply turn the BST into a set and use the regular method to solve two sums. I don't think using BST is going to make it easier, going to make the solution any easier. Now you could turn it into O1 in space. All right, the memory usage. What's the memory usage? 21. Yeah, so the memory usage. The only benefit of using BST is to save memory usage. So this is ON in time and ON in space. We get 84. Okay, how do we do it, say, in O1 space? O1 space, we have to use BST. Okay, so I mean, like a very stupid way is just to ON log n, right? ON log n to not use space. DFS node, right? So we're gonna have a node, and we're gonna return a Boolean value, right? So for each one, we're gonna have search, right? For each one, we're gonna search, and the DFS basically just goes through each. We're gonna have two functions. We're gonna have search, and a search we have to always search from the start, right? We have to always search from the start, and we can also add a little bit more, like a minimum value and we can have the min value and we can do that. So I think like the min val, right? So we just keep going, and then min val equals math.inf, right? And then import math, and min and max, and we say node equals root, while node equals node.left, right? Blah 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 until node min val equals min val val, and then keep going. Now this we get the min value, right? And then we also get the max value. It's going to be minus and no max value. I just do all the mins and max, and that's going to be the right. Right, so we get the min value, we get the max value. And now we can go. Right, now we can go. So we're going to say, actually, it's going to be solved, right? We're going to say def search. We have a search function. We have a node, going to be optional tree node, and target, and link. Right? So we say target is if node, if not node, return false, right? Otherwise, we say, I'll just say if node, and then at the end, return false. If node, if target is larger than node.val, search node.right, return search node.right, else return search node.left, right? And if not null, return false. So this one can actually be simplified. Say this, say return this if else search on the left. Right? So this is search, and after search we have, let's call it solve. So we have the initial value. If node, right? If node, we say if node.val target equals k minus node.val, right? We say if target is larger than max value, right? If the target is larger than max value, so my current is too small, then we say return solve node.right. If target is smaller than mean value, which means I'm too big, right? Then return solve node.left. If I'm in between, then we return solve node.left or solve node.right. And blah blah blah. If not null, then we return false. Right? Then we just return solve root. Alright, let's try this. That's more convoluted. Alright, let's see if this one works. False. How about 9? Ooh. How is this one? Node. Return. Oh. If node. Oh, I forgot to return true. Ay. If target equals node.val, return true. I forgot to return true. Otherwise, I'm going to return this if, yeah, forgot to return true. Oh, it's still not right. What? Target equals k minus node.val, right? And then if target is larger, then the target is too big, so we only search on the right side. Target is too small, we only search on the left side. If the target is in between, then we don't know which side to go, so we do the left side and do the right side, right? And I'll keep going. Next target, k minus, What's the problem? I want to solve. Oh, you didn't call search. Hold on. Target is, we can call this is true. And then, oh, you need to search, man. What what the heck? Um, oh, we can do these two. All right, these two is fine. So like we already know the target is not going to be in there. Otherwise, we're going to search, right? We're going to say if target is not equal to k and search. Actually, search we don't need. Oh, which is a root. I will search from root and target, right? So target is not equal to k, and not equal to k, not equal to node val, node.val, and search return true. Right. Otherwise, then we have to keep searching. Search missing. Well, I forgot the target. Yeah, I forgot a target here. Target larger than node.val. Turn this. Make it more explicit. And last one is, I think I should do elif. And last one is else. Turn this. Okay. Let's do a 213. Let's do a 213 and 9. That should give us false immediately. 1. I think it's right, but let's just look convoluted. So this is O log n to find both. And then search is log n. Solve is on. So on log n in total. Pending, judging, accept on log n. Yeah, it's slower. The memory usage is the same. Did I miss something? Probably I missed something. So this is trying to use, right? This is trying to use BST and without extra space. So on log n. I mean, the space complexity can be reduced if we use, let's say, I don't know. What's this question aiming at? Like, what's your target? I have no clue. I have no clue what they're trying to get. $653. 53. All right, what are we trying to do? Iterator. Using iterator. Ah, what's that? Yeah, it doesn't. You don't have to. We can do it in one pass. That's fine. Interviewer expects this solution. Elements are sorted. iterate in order elements with OH space complexity. Elements are sorted 2 pointers to search a pair. Right pointer to the right element. Hold on. Iterators. I mean, just pointers, right? So we grab the pointer from the binary search tree and what? Push left. Push right. Next left. Next right. ST search tree left, search tree right. Push left, push right. While root. So we push the left nodes into the ST left, push the right nodes into ST right. Okay. So append root and everything to the right, everything to the left. Now what? Left and right equals the next. I'll pop out, that's the smallest, the right is the biggest, which is true. Oh, hold on. The next has push left in it. Alright, so hold on. So we have a root, and while root, we append the root and then we go for the left and go for the left. That's what push left, push right means. Given any root, we push all of its left into it. So we call next. So after we call next, we get a node, right? We get the node as a current end of the list, and after we grab it, push left. We need to push something that's smaller than this. All right, so everything is left, 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 left. I'm gonna take this out. We need to get the next smaller. So node dot right. We push left of node dot right. Push left of node dot right into it. So that's how we get iterators on both sides. On both sides, and this can be node dot left. Yeah, that's the next largest value inside. Push left, push right. And then every node is visited once. That's ON. This is ON solution. While left is smaller than right. If this is true, if it's smaller than k, which means we need bigger left. So we find the next left, or we want the smaller right. Because the root is inside the array. The largest. All elements are unique. All right. Do you have concerns about this using iterators? Yeah, but they're not used. Yeah, you can do that. I prefer getting everything and then do this, but I think it's fine. All right. But how do you avoid this situation? For each I BFS. Uh-huh. Oh, we create a new set at each root. Wait, what? No. No, this is doing iteration. It doesn't. It's recursion, but you write it. Oh, but it's BFS. You use BFS. Doesn't matter. You just iterate through BFS. If it's innes, I turn true. I think it's gonna fail if we have like 10. I don't know. I feel like it's gonna fail. Right? I just say k minus this in. Oh, I don't add it first. Ah, that's the trick. I check first, and then I add it. That's the trick. Okay, so the idea is to use iterator. I actually don't know about this iterator idea. Push left, push right, next left, next right. I mean, the idea is just to get next right, next. This is O and log n, but that's not what the interviewer wants. The interviewer wants this. This is what the interviewer wants. BST iterators, courtesy of this. All right. And also do solution 4. Solution, let's call it solution 1-1. Right, 1-1. 1_1. So it's same as solution 1, but we can embed the checking in the DFS. Right. So what we're gonna do is just gonna return Boolean value. Right. And all right, let's try not to see this. So it's gonna return Boolean value. So if node, we're gonna first check. We say if k minus node.val in vals, right? Then return true. Yeah, because it doesn't matter if the front we don't hit it, the end we won't hit it. Else we're gonna vals.add, and then we return DFS node left and or DFS node right. And I don't have to do all this. I'll just say return BFS node. All right, let's see. This one pass. Can't believe I have a wrong answer. What is this wrong answer? Ah, yep. As expected. Oh, we can do console. Use example. Yeah. Wait, there's no node. Root. See? I told you, you can always try, run it first before you submit. Output true, false, true, false, true, true, false, true, false, true. Yeah, this is correct. All right, now we focus on this. So BST iterator. So I'm going to follow that. So we have push left. I like to call node. Optional tree node. Don't return anything. Oh, and also node list, right? Be a list. And then we just say while node. Node list dot append node dot val, and node equals node dot left. Push all the way left. Right? And then we're gonna say push right. Same thing, but we're gonna go all the way to the right. And then next one's the next left. We're gonna have node list, right? This one I'm gonna return a integer. So next to left, we're just gonna do val equals node list dot pop. All right, that's the one we're gonna return. After that, we're gonna say push left. All right, we popped. Oh, we should push in the node. Ah, this is going to be a list of tree node. The list of tree node. We're pushing the node, not the value. So we're pushing the node. Pushing the node. So when it pop out, it's going to pop out a next left, right? A node pop out. And after we pop this one out, we need to push in the value that's bigger than next left, but smaller than the other ones inside the node list. So which is going to be next left or right, and node list. And we return now dot value. Yeah, we can get the value, but we have to pop out is actually, let's just call it, I wouldn't call it node. We're going to use node. Node equals this is going to be node, and this is going to be node. I'll copy and paste this whole thing again. But this time we're going to call it the next right. And node list pop. After pop, I'm going to push right. And this is going to be node left. Right? Okay. So I'm going to say left nodes and right nodes, right in the list for left and right. And then we're going to call push left nodes, no, root first, and then push right, root right nodes. Right, so we push left and right, and left right equals next left nodes, next right nodes, while left smaller than right. Now, left and right are the values, right? So left and right are the values of the iterators going from both ends of the BST towards the center. So while left is smaller than right, we say if left plus right is equal to target, return true. Otherwise, if left plus left is right is smaller than k, so too small, then left equals next left, left nodes, else too big, right equals next right, right nodes. And if nothing, return true, we're going to return false at the end. All right, I'll try this. Same thing, I'll run code, and I'll comment on this. I never tried this one before, but never heard of BST iterator before. Very neat technique. Thanks. All right, so this is the binary. I don't think I've done this before. Oh, I've done this before. I've done this before. In order traversal. You're right. This one is slightly different. So I think for this, I only need half of this. We only need, we only need a push left. Yeah, we only need push left. I have done this before, and I have a solution anyway. Int and none type. That is not what I had expected. What has gone wrong? Oh, I forgot to return. Return all that out. Yeah. This has to return node.val. Okay. Yep. So submit this. Iterator. Oh, iterator is the fastest. Okay. on time, right? oh space, and we run at 72 seconds. Optional here, optional 2 lines, too many lines. Okay. What did I do? From stack, I push all the left in, and then next will pop, and the rest node.in right, on node, stack.pan node. Yeah, there's a push left. There's a push left. There's a push left. I solved it myself. Huh. Yep. 8 months ago, and I forgot. Yeah, I just completely forgot about this iterator thing. It's good. It's good. Kind of refresh the memory. All right, that'll be it for today. I think I still need to shrug off some of the rust from yesterday. I didn't do very well today, honestly. See you guys tomorrow. Adios.